Earlier, we only solved a single linear difference equation. Now we're going to look at systems of linear difference equations followed by systems of differential equations. So let's begin this by considering the example that we had solved earlier, and that is that yt plus 2 minus 8yt minus 1 plus 12yt equals 0. In operator form, this is expressed as e squared minus 8e plus 12 all times y of t equals 0. We introduce a new variable, xt equals yt plus 1, which in operator form is just e times yt. So we introduce that, we call it xt plus 1 equals yt plus 2. So in other words, if we have xt equals yt plus 1, which in operator form looks like this, then xt plus 1 equals yt plus 2. We can rewrite this equation, number 1, as xt plus 1 minus 8xt plus 12yt equals 0. A pair of first-order linear difference equations arises, and we can write those as xt plus 1 equals 8xt minus 12yt, and the second one as yt plus 1 is simply equal to xt. In matrix notation, we get that xt plus 1, yt plus 1 is equal to the matrix 8, 1 minus 12, 0, multiplied by xt, yt. The same principles can be used to convert any nth order difference equation set to a system of first order equations. So if we look at n equations, then, or an nth order difference equation, we get that y1t plus 1 is equal to a11 y1t plus plus a1n ynt, and then we have a second variable yt, and we have yn as well. So we have n different variables, and all of them are expressed in terms of a first order equations. In matrix notation, we have that capital Y. We'll use that to denote a matrix, capital letters namely. Yt plus 1 is equal to capital A yt, where the A matrix is given by these elements a11 a1n in the first row, a21 all the way to a2n in the second row, and in the nth row we have an1 all the way to ann. In the non-homogeneous case, an nth element column vector can be added to the right-hand side of number 5. So if we had a k, let's say, which is a column vector of n elements of right-hand side values, which in this case would be added to the end here, and we'd add that k over here. All right, but that really doesn't change the solution procedure. A solution to this equation that we just mentioned, yt plus 1 equals ayt, is found in the single equation case as y1 equals a times y0 equals c0, which c0 refers to the initial conditions. Then y2, so the second time period, a y1, where here the subscript denotes time, a times a y0 is a squared c0, and then for the general case of yt at any given time t, we get that it's equal to a times capital yt minus 1, what it was in the previous period, equals to a to the power t times y0, which is just a to the power t times c0, where c0 is distinguished from y0 in the terms that y has to be determined, whereas c0 refers to the initial conditions. So let's let a0, so a to the power 0, which is a 1, be the identity matrix such that yt is equal to at c0 holds for all t from 0, 1 throughout higher values of time. To get values of yt for high values of t, a must be raised to a high power. which could create problems even though A is a square matrix. For example, we'll find when we're talking about stochastic dynamic programming that we have a matrix where all the elements are less than 1 and greater than 0 because they're probabilities. And if we multiply that matrix over and over again by itself, it'll deteriorate to 0. And you can think about that on your own. Calculation of AT, therefore, is straightforward only if A is a diagonal matrix. So then yi t plus 1 is equal to ai yi t for any given equation in that system, for any given I. It is unlikely that system 5 would have that property. The question then is, can variables y be transformed so that A is a diagonal matrix? Well, it turns out that it can be. So we let Z be a vector of elements Z1 through Zn that's connected to the y's, the small y's, the individual y's, by this equation y, capital YT, equals P times ZT, where P is an n by n matrix. So given equation 5, we then rewrite that as P times ZT plus 1 equals A, our original A matrix, multiplied by this n by n P matrix, multiplied by that matrix, vector ZT. So ZT plus 1, therefore, is given by P minus 1. So what we do is we pre-multiply the left-hand side by P minus 1 to get rid of that P. And we do the same thing on the right-hand side, and we get P minus 1A times P equals ZT, assuming that P is non-singular, which means that the determinant is not equal to 0. Then we define a new matrix D as equal to P minus 1AP, which implies that ZT plus 1, that column vector, is now equal to that matrix D times ZT, what the column vector was in the previous period. So if P is chosen so that D is diagonal, the solution to this equation, 7, would be straightforward. Why? Because from 6, we get that ZT equals DT times Z0. Since Y0 equals PZ0, then Z0 is P minus Y, P minus 1 Y0, so the inverse of P times Y0, and ZT is equal to this diagonal matrix D to the power T, so we have to multiply the diagonal matrix now instead of the A matrix to the power T, so T times, multiplied by the inverse of P times Y0, the first values of the y's that we want to solve for. Finally, from yt equals pzt, we get that yt is equal to that matrix P pre-multiplied by d to the raised to the power t times the inverse of P, all times y of 0, which is written the same way, P d to the t inverse P times C0, where these C0 are the initial values of y. If we could find a non-singular matrix, P, that would transform A into a diagonal matrix D via this transformation P, the inverse of P times A times P, then the solution to the original problem, 5, would easily be found utilizing the tth power of D, pre-multiplied by P and post-multiplied by the inverse of P. Rather than multiplying A by itself, T minus 1 times, we would need one inverse, the inverse of P, and then two matrix multiplications, P times D to the power T and P times D to the power T multiplied by the post-multiplied by the inverse of P, in addition to raising each of the n elements in D to the tth power. So you see, that's why we want to use that diagonal matrix, because it's easy to just increase or raise the power of diagonal elements to a power t than it is to try and take a whole matrix and raise it to the power t. So how does this work in practice? Well, first off, the eigenvalues of A are the diagonal elements of D. So the eigenvalues of A are simply the diagonal elements of that D matrix. Then second, the columns of P are equal to the eigenvectors of A. So solving a system of linear difference equations is more problematic if two eigenvectors of A are equal because P is non-singular. This rules out the case of repeated roots of the characteristic equation of A. Now, modifications are available to deal with this problem, but they're beyond the scope of this course. And I should note that we will encounter a similar problem when we consider stochastic dynamic programming. So let's turn now to systems of linear differential equations. It turns out that the same solution method can be used with a system of linear differential equations as was the case with difference equations. So let's consider in operator form the following problem. D squared minus 3D minus 10 multiplied by yt, where yt now is a continuous variable, is equal to 0. And again, for the non-homogeneous case, we can just add on the right-hand side throughout that vector k of a column vector that has those right-hand side or non-homogeneous component to it. So what we do again is we let x equal dy dt, or y dot. X dot then is dx dt, or it's equal to d squared y dt squared, or double dot over the y. So we rewrite this equation that's in operator form as dxt minus 3x minus 10y equals 0. We rearrange 10 and 11, so we get these two first order differential equations. Dx dt equals 3x plus 10y, dy dt equals x, which in matrix notation is given as x dot over y dot. That vector is equal to this matrix 3, 10, 1, 0, 3, 10, 1, 0 multiplied by x, y. The general representation for the homogeneous n equation, first order system, is then given by, and now we've replaced the x's with a y2 and a y3 and a y all the way up to yn. And we take the first derivatives with respect to time, which means we put these dots on top, and we get a11 y1t plus dot 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 a1n ynt. And for the final one, if we have n equations, we have yn dot equals an1 y1t plus dot 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 plus ann ynt, which in matrix notation we write as y dot equals A, so matrix A multiplied by y. So if A is a diagonal matrix, then a typical equation in this system is just simply given by y dot I, where I refers to the ith variable, is equal to di yi. This would have a solution of the form yi 0 edi to the e to the power dit, where yi0 is some known initial value of yi. The elements of the diagonal matrix are the eigenvalues of the matrix A, just as above, and thus a solution can be written as yi equals yi0 e to the lambda it, where the lambda I is the eigenvalue here. And we define a new n by n diagonal matrix as follows, where this is a capital alpha lambda, so e to the capital lambda t, so this is a matrix, is given by these elements here. So e to the power lambda 1t, e to the power lambda 2t, all the way to e to the lambda nt along the diagonal with zeros in the off diagonal. So this matrix here is a diagonal n by n matrix. Then the solution to 13 can be expressed as y equals e to the capital lambda t y0. If A is not diagonal, we use the same transformation as we did in the case of difference equations. Namely, we let y equals p times z with y0 equals p z0, and as a result, the dy dt vector of dy dt's is equal to p times that vector z dot, where the z dot represent dz1 dt, dz2 dt, etc. Then equation 13, or the system of equations represented by 13, becomes z dot, so dz dt equals to the inverse of the P matrix multiplied by A times P times Z. And we define D as being the inverse of P, pre-multiplying A, and then post-multiplying by that matrix P. Using distinct eigenvectors of A to form columns of P, D will be a diagonal matrix whose diagonal elements are the eigenvalues of A. So then we have Z dot is equal to D times Z, and that will have the solution that Z equals e to the capital lambda T times Z0. And by substitution, 13 will have the following solution, where y is equal to P times e to the capital lambda T post-multiplied by the inverse of P, and then post-multiplied by that vector of initial conditions, which, or initial time period, which we then transform into the initial set of values for the y variables C0, and we get this equation 17, which is the result. So let's look at this example. A equals 7, 3, minus 4, minus 1, with y0, 4, and 8. This is the initial conditions, and in system notation we get y dot equals A times y. Now the trace of A, which is simply the sum of these elements, so 7 plus 1, plus a minus 1 rather, gives you 6, and that results in an unstable solution, but nonetheless we get a solution, and stability is something we have not looked at, and we don't want to consider it in terms of vector and matrix notation, but we'll look at that in terms of phase plane diagrams a little later on. So the eigenvalues of A are determined from the original A matrix by subtracting along the diagonal this lambda and then finding the determinant of that result and setting that equal to 0. We find that lambda 1 equals 1 and lambda 2 equals 5. If you cannot recall how this is done, this was done in Economics 350. The eigenvector associated with lambda 1, which we denote V1, is derived as follows. We take the matrix A and we subtract lambda 1 times I from it, which is how we get these minus lambdas up here. Multiply by V1. V1 has these unknowns, V11 and V21, that we're going to solve for, and we just do this here. We subtract the identity matrix from the A matrix, and we post-multiply it by that vector and set it to 0, which gives us 6V11 minus 4V21 equals 0, and 3V11 minus 2V21 equals 0. Two equations, two unknowns. We solve for the V1 equals 2 and the V2 equals 3, and we find that the vector V1 is 2, 3. Now we can do the same thing with regards to the other eigenvalue, and we find that the eigenvector is given by 2, 1. Then P is given by these two eigenvectors, 2, 3 and 2, 1. We take the inverse of P and we find that it's equal to minus 1/4, 3/4, half, minus a half. And then the solution is found using this equation here, and we just fill that in. So y is equal to this P matrix, which is this one up here, 2, 3, 2, 1. Then we have this matrix here, e to the power t, e to the 5t, which we found up here. All right, these are our eigenvalues. These are the eigenvalues here. We multiply that, post-multiply it by the inverse of the P matrix, which is this one, and then by the initial conditions V 4 and 8. That gives us these two equations, and that is basically our solution to y1 and y2. And as I noted, we're going to investigate stability issues using phase diagrams. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.